In this video lesson on moles, we will be looking at what is the mole and how big the mole is, including the key lesson vocabularies. Also, we will look at examples on how to calculate molar mass and moles. First, what is the mole and how big is the mole?
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amedeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is... anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us.
Now, let's look at some of the key vocabularies. In moles, we'll look at the definition of mole. a mole of a substance is defined as 6.022 times 10 to the 23rd power representative particles of that substance, and also as the SI unit for measuring the amount of a substance. So the examples you have here are that of mercury 2 oxide, sucrose, copper 2 sulfate pentahydrate, copper, sodium chloride, as well as sulfur. Each of these substances are all 1 mole of the respective substance, and each of these 1 mole of these substances contain 6.022 times 10 to the 23rd power. Now the next is the Avogadro's number. The Avogadro's number is defined as the number of representative particles in a mole, which is 6.022 times 10 to the power to the 23rd power. It is called the Avogadro's number. The representative particles are defined as a species that represent a substance. It could be atoms, ions, molecules, or formula units. Each of those terms represents representative particles. And the last term we're going to look at is molar mass. Molar mass is the mass of 1 mole of a given substance, and is usually expressed in grams. Now, in this video, we're going to look at how to calculate the molar mass of a given substance.
How to calculate molar mass in 3 easy steps. First off, there are many other names for molar mass. They all tell us the mass of 1 mole of a given compound. The key is to find the atomic mass for elements, and that's right below the element symbols. Think of atomic mass as molar mass for an element. Let's find the molar mass for carbon monoxide. So we go to the periodic table, we find carbon, and we find oxygen, and we see the atomic mass there right below the element symbol. To find the molar mass, we add those 2 numbers together, and we add the units, gram per mole, and we're done. We've found the molar mass. You may have noticed that in the previous example, I rounded to 2 decimal places. Make sure you know what your teacher requires. Let's do an example, H2O. You can think of H2O as being made up of 2 hydrogen atoms and 1 oxygen atom. So we can go to the periodic table, find the atomic mass for hydrogen, and then for oxygen, and then we'll add the 2 hydrogens plus 1 oxygen to find the molar mass for H2O. But there's a quicker and easier way to do this. We can write the atomic mass for hydrogen and multiply that by 2, and then add the atomic mass for oxygen, and that'll give us the molar mass for H2O. Let's try another, NH3. So first, we look up the atomic masses on the periodic table. We have 14.01 for nitrogen and 1.01 for hydrogen. And then we're going to multiply that hydrogen by 3 because there's a subscript of 3 after the H. Once we do that, we add everything up and we have the molar mass for NH3. Pause and try these on your own. So check your work and make sure you included the units grams per mole. Just to mess with you, I included parentheses in the third one. So how do we deal with this when we have parentheses? We'll use the same process as we've been using. So first, I'll write down the atomic mass for each of the elements. And then I'll put the parentheses around the elements just like they show up in the formula. And because I have this 2 right here, I'm going to multiply everything by 2. Once I do that, I then have 40.08 plus 17.01 times 2, and then I'll just add these 2 numbers together to get the molar mass for calcium hydroxide, CaOH2. So pause and give these 2 a try. So check your work. If you're having problems, in the description there are links to full videos for each one of these compounds. There's one more type of molar mass we need to learn to calculate, and that's for what's called a hydrate. This is copper 2 sulfate pentahydrate. Penta means 5, and the little dot means those 5 water molecules are around the copper. To calculate the molar mass, we'll first find the molar mass of the copper sulfate, and then we'll find the mass of the water. Once we have those, we'll add the copper sulfate to 5 times the mass of the water molecule. That's because we have 5 water molecules. We add this all together, and that's the molar mass for copper 2 sulfate pentahydrate.
Now, the last video is going to show us how to calculate moles. Some questions in moles requires you to first of all calculate the molar mass, whereas some questions simply requires you to convert from moles to particles or particles to moles. So let's look at these examples.
In this video, we're going to cover what the term mole means and see how we can use this formula to convert between moles, mass, and relative formula mass. Now, the term mole is a bit weird, but really it's just a unit we use to measure the amount of chemical that we have. So just like we measure distance in meters and time in seconds, we can measure how much substance we have in moles. And 1 mole of any substance is just the amount of that substance that contains 6.02 times 10 to the 23 particles, with particles referring to atoms, molecules, ions, or even electrons, depending on which substance you're talking about. So if we had a little pile of carbon and we were told that it contained exactly 1 mole of carbon, then there must be 6.02 times 10 to the 23 atoms of carbon in that pile. We call this number Avogadro's constant. And the reason it's this specific number is that the mass of that many particles of any substance will be exactly the same number as that substance's relative atomic or formula mass in grams. So our little pile of 1 mole of carbon would weigh exactly 12 grams, because carbon's relative atomic mass is 12. Meanwhile, 1 mole of oxygen, which has the relative formula mass of 16 times 2, so 32, would weigh 32 grams. Or 1 mole of CO2, with a relative formula mass of 12 plus 16 plus 16, and so 44, would weigh 44 grams. But in all these cases, there would be 6.02 times 10 to the 23 atoms or molecules. Because of this rule, we can create a formula which tells us that the number of moles in a sample is equal to the mass of that element or compound divided by its MR. So if we want to know how many moles there were in 42.5 grams of ammonia, we would do 42.5, which is the mass, divided by 14 plus 3 times 1, so 17, which is the MR of ammonia. And this would give us 2.5. So we know that there are 2.5 moles of ammonia in the 42.5 grams. We can also rearrange the formula to find the mass if we were given the number of moles. For example, what's the mass of 3 moles of carbon dioxide? Well, this time we'd multiply our 3 moles by the MR of CO2, which is 12 plus 2 times 16, so 44, which gives us 132 grams of CO2. We can also work out the mass of a particular element within a larger compound, like the mass of carbon in 3 moles of carbon dioxide. For this, all we do is take the number of moles, which is 3, and multiply it by the MR of the carbon, which is 12. So 3 times 12, which gives us 36 grams of carbon in our 132 grams of carbon dioxide. And if you wanted to go one step further, you could subtract that 36 grams from the original 132 grams to find that there must be 96 grams of oxygen, because we can see that CO2 is only made up of carbon and oxygen. Now, the last thing we need to mention is that when you look at a chemical equation, you can think of them in terms of moles. So for this equation, we can think of 1 mole of magnesium reacting with 2 moles of hydrochloric acid to form 1 mole of magnesium chloride and 1 mole of hydrogen gas. And you should think of these as ratios. So if we started with 2 moles of magnesium, we'd have to react it with 4 moles of hydrochloric acid, and it would produce 2 moles of magnesium chloride and hydrogen gas.